Welcome to my talk about SYN flood defense and programmable data planes. Unfortunately, SYN flooding is still a very serious problem on the internet because it is an inherent flaw in the TCP handshake protocol. You can oftentimes read in quarterly denial of service attack reports, for instance, here from Kaspersky, that SYN flooding is among the top-rated used attack traffics. And because it's a flaw in the protocol, you can't just change it, meaning you always need protection for your end nodes and your networks. And because the attack traffic also increases, your solutions need to scale. Of course, there are solutions. For instance, in pretty much every network stack, there is some mitigation method. But of course, these solutions do not scale because they only protect this particular end node. You can use your favorite packet processing framework, but then the solution is not portable. It will only work for this framework. Or you can use commercial solutions like traffic scrubbing centers, but then the solution is closed source and probably quite expensive. So we looked at moving this mitigation to the data plane, because then you can do the mitigation anywhere in your network. You can do it very efficient and also very flexible. So I want to talk about SYN flood specific mitigation methods and how we implemented them using before I conclude with the talk. You can use SYN flood specific mitigation methods in two different scenarios in regards to deployment. You can use it on the end host, but then of course, as I already said, the solution does not scale because it only works in this particular node, and also it takes away resources from the server that, for instance, should serve a website. Instead, you can deploy the mechanism somewhere in your network or in the cloud as some sort of proxy, and I will call this a SYN proxy for the rest of the talk. And this way, then you can protect multiple servers or even whole networks against SYN flood attacks. And the task of this proxy is to intercept TCP flows and distinguish malicious traffic from legitimate traffic, and only forward legitimate traffic to the servers that are being protected. And now, depending on the concrete method that you use in programmable data planes, different challenges arise that I want to talk about. And specific, we want to talk about SYN cookies and SYN authentication that I'm going to introduce on the next couple of slides. SYN cookies are well known, and they are a cryptographic hash called a cookie that is bound to the connection flow. And what happens here in this setup, the client will send its initial SYN packet to the proxy, and the proxy will not keep state, but instead calculate a cookie and send it back. And only once it receives the acknowledgements and verifies the cookie, the connection is handled as legitimate. And because we have this proxy setup, we now need to also create a second connection with the server. So we have then one connection between client and proxy and one between proxy and server. And this also means that the sequence numbers that are being used on the left side and on the right side will not match, meaning we need to store the delta and translate all subsequent communication between client and server using this sequence number translation with our calculated delta in the beginning. Another problem is that the initial data segment, which is usually sent immediately after the first acknowledgement or with the first acknowledgement, cannot be forwarded immediately because the connection between proxy and server is not active yet. If you look at SYN authentication, the idea here is quite different, because here we explicitly interrupt the initial connection attempt and only whitelist once a challenge is complete. So here we receive the SYN and see it's not yet whitelisted, so we send it back, and only once the client finishes the handshake, we whitelist the connection and terminate the first connection. This can also include not just the handshake, but even a higher layer connection. So the client needs to prove that it wants to initiate, it can initiate a higher layer connection before the proxy terminates, and then whitelists any future connection attempt. And the idea here is now that because you can whitelist all future connection attempts, you can immediately forward even the initial handshake to the server, so you do not need any translation for the remainder of the time. So if you compare these two methods, you can see that for SYN cookies, we have to modify every segment because of the sequence number translation. But on the upside, the method is completely transparent and does not involve any sort of reset. On the other hand, we can only encode a limited amount of options. If we look at the amount of state that you have to keep for SYN cookies, we also need to keep it per flow because of sequence number translation. On the other hand, for SYN authentication, we can aggregate state and reduce the memory footprint because we can whitelist, for instance, based on subnets. Now, on the other hand, here we need to look up for every single segment this amount of state that we have. Now, if you look at implementing these methods with P4, the program core is the same independent of the method and the target that we use. So here we can pass the packet up to including the TCP header, and the rest of the program simply behaves like a layer 2 forwarder. Now, depending on the concrete method that we use and depending on the concrete state that we have to modify the packet a little bit, meaning, for instance, if we receive a SYN packet, we need to send back a SYN acknowledgement packet, for instance. And all state that we maintain, for instance, for the whitelisting or sequence number translation, is being stored in match action tables. Now, depending on the concrete target that we use, we have target-specific changes, meaning, for instance, the architecture model is different, then of course we have to adapt even the program core, or because we need to calculate the cookie value, we need a cryptographic hash function, which of course is not part of standard P4, but can often be made available through an extern. And this is also one of the challenges that I want to talk about, because cryptographic hashing is not trivial in P4, but it is possible on several targets, as we've shown in our paper last year at this workshop. Because, for instance, you can add externs on software-based targets, for instance, using DPDK or network processing units that you can often program and just add an extern. For FPGAs, you can, for instance, modify the architecture and add a hashing IP core somewhere in the pipeline. And for ASICs, of course, you can't change the behavior of the ASIC, so you need to be more creative and offload this functionality to another node. So clearly you see we have portability issues here that arise depending on the concrete target that we are using. The second challenge that I want to talk about is whitelisting, because you have to somewhat maintain the state that is being kept in the data plane. And for this, of course, you need a control plane. You usually don't want to just whitelist someone forever, so you at some point need to evict some outdated entries. You can also use something else, but matching tables. So you can, for instance, use Bloom filters for this, built from register externs. But of course, then you again have architecture-specific problems or challenges, because these might require more resources that are limited, or the performance is different to match action tables, and this might be a problem for you. To conclude the talk, I want to briefly talk about what else we've have included in the paper. We've done an extensive performance evaluation of our different targets that we imported the P4 solutions to. We looked at the software-based DPDK solution using the Tapas framework. We looked at the Agilio SmartNIC processing unit, network processing unit, and also at the NetFPGA Sume. We also did a case study by looking at the Linux network stack and looked at how SYN mitigation is handled there. And lastly, we also did our own implementation using a software packet processing framework based on libmun DPDK, meaning we implemented SYN mitigation not using P4, but instead just raw packet handling. And here the interesting comparison you can see here, because it took us roughly 6 months to have a working prototype using libmun DPDK, whereas it only took us roughly 2 weeks to implement the P4 solution. So that's quite a drastic difference and shows the benefits of P4. And also it only took us a tenth of the number of lines of codes. And of course, the solution in P4 is more portable, because the DPDK solution only works in DPDK, whereas the P4 solution works, for instance, on DPDK, but also network processing units and FPGA. Now, to conclude my talk, I want to say that SYN mitigation using P4 and programmable data planes is not just possible, but it's also surprisingly easy to implement. And because it's P4, it also scales nicely, because you can just get some more potent FPGA that is, for instance, for 100 gigabits, and then you have a solution that works for 100 gigabits. And also it's portable, meaning you're not just bound to one target, but of course this is limited, because it's depending on or it requires a cryptographic hash function to actually have the mitigation methods work securely, so that they can't be circumvented. And also a small conclusion about the usability of P4. Yes, it was easy to implement, but depending on the concrete target and whether you port the solution to a concrete target, you still require domain-specific knowledge because sometimes you just have to debug the target, and depending on whether that's written in C or Verilog, you need to understand the device. Thank you very much.